So today we'll be looking at heat capacity and specific heat capacity. First, what is heat capacity? Heat capacity or thermal capacity can be defined as the quantity of heat energy required to raise the temperature of a body. The SI unit of heat capacity is joules per Kelvin. Heat capacity, the formula for heat capacity is C equals to MC. So what is heat capacity? Heat capacity of a substance is the amount of heat energy required to change the temperature of a unit mass of substance by a unit temperature.
Why did you skip? Why are you skipping those ones?
Mathematically, Q likely proportional to M theta. So this is how to write the formula where M is the mass of the body is in kg, theta 2 minus theta 1 with the temperature change in degrees Celsius or Kelvin. C is the constant which depends on the nature of the material that makes up the body, and it is called the specific heat capacity of the body. The SI unit of specific heat capacity is C of the SI unit was kilogram Kelvin. So so these are some examples of specific heat capacity. So this question says, explain the statement. The specific heat capacity of copper is 400 joules per kilogram degree Celsius. Solution. This means that 400 joules of heat energy is required to change, increase or decrease the temperature of 1 kilogram of copper by 1 degree Celsius. So let's look at some experiments. Specific heat capacity can be measured by two methods. One, method of mixture, and the electrical method.
What's the essence of scrolling? What about the diagram that I did?
I want to explain one experiment.
Okay. You can continue talking while you're looking for the experiment.
Okay. So this is specific heat capacity of a solid by electrical method. Here you can see that two holes are bored, after which the block is weighed. Then an electric heater and a thermometer is inserted in each of the holes. A little oil is added to establish good thermal contact with the block. So the large jacket helps to prevent heat losses. For further explanation, the initial temperature of the block is noted and the electrical heater is switched on, and current are allowed to flow for some time until the temperature rises by about 15 degrees Celsius. The exact time of flow of a known current is measured with a stop clock, and the thermometer. So these are calculations under specific heat capacity. Example 1, this is a NECO/SSC 2007 question. So the temperatures of water from tap A and tap B are 25 degrees Celsius and 75 degrees Celsius respectively. If a mixture of water at 40 degrees Celsius is required, calculate the ratio of the mass of water from tap A to that from tap B. So before you start solving everything, you give out your parameters so you won't be confused. So heat lost by water from tap B equals to heat gained by water from tap A. So this is the formula that you use to solve it. So
Let's how you got it. Don't skip that.
since C is the same on both sides, MB bracket theta 2 minus theta equals to MA bracket theta minus theta 1, MB bracket 75 minus 40. Then MA will be 40 minus 25. So 35 MB equals to 15 MA equals to 35 equals to 7 MB. 15 ratio 3 MA equals to.
You see, you have not, you do not know the calculation of what you have done because you are just reading from the screen. It does not show you. Let's see.
Example 3. A laundry iron rated 400 watts has its temperature increased by 40 degrees Celsius after 2 minutes when connected to an electric mains. Calculate the heat capacity of the iron. So first you give out your parameters. P is power, that is 400 watts. So theta 2 minus theta 1. Since there is no other theta, you now put 40 degrees Celsius. 40 degrees Celsius. So that will be your theta. Then for the time is 2 minutes. To convert, you convert this minutes to seconds. Then you multiply 2 by 60. But that will be 120 seconds. So the formula you use to calculate this is PT equals to MC bracket theta 2 minus theta 1. Your power is 400.
Let's move to another slide. Okay, I'll explain that.
Your power is 400 watts. Then your time, remember you calculated 2 minutes to seconds. That will give you 120 seconds. So equals to C times 40. 40 is your temperature, that is your theta. So C will now be equals to 400 times 120 divided by 40. You divide both sides by 40. That will be 1,200 joules per Kelvin.
Okay, you're done now. Let's see the next slide. What do you have on the next slide? Okay, thank you, Master Honor and Tony. Okay. Okay, next person. Hello. Check for your. Just quietly. Okay. Master Okase Kose. Okay, let's have you.
So going
In 5 minutes.
so good morning everyone. My name is Kusi and I'm a student of STR College, year 11 physics. And today the topic is wave. We're going to be talking about the production of wave, propagation of wave, terminologies and diffusion of wave. We're not dwelling on the deep side of wave, but just the basics. The objective for today is to understand the concept of wave and the wave motion, to be able to explain how waves are formed, to be able to establish questions on waves and get diagrams. Very important for us to understand that. To be able to derive the wave equation and finally to be able to solve questions of wave.
Please, you're backing the camera too much. You can make use of the roller too.
Now, the definition of wave. A wave is the disturbance that travels through a medium, transferring energy from one point to another without causing any permanent displacement of the medium. Wave motion. Now, wave motion is the movement of wave transmitting energy due to the wave motion is the process of transmitting motion of a wave due to the disturbance in the absence of material medium or through a material medium without displaying the medium. Now, classification of wave. Classification of wave can be based on mode of propagation, or it can also be based on medium of propagation. Now, this is based on medium of propagation. Mechanical wave and electromagnetic wave are the classification of wave based on medium of propagation. Mechanical wave, these are waves which require material mediums for them to be propagated, e.g., water wave, sound wave, wave on loop or screen. Now, explain this by saying the material medium we're talking about is either it can be in solid, liquid, or gas. Electromagnetic wave, these are waves which do not require material medium for propagation, e.g., light waves, radio waves, X-rays, and gamma rays. You can remember these types of electromagnetic waves by a small by ribose G, meaning all the different types of electromagnetic waves. Production and propagation of wave. The disturbance of any material medium produces mechanical wave, as we all know. By disturbance, we mean the same energy it impacts into the medium, and the energy is transferred from one particle to another as the particles are vibrating about their equilibrium position. For example, when you throw a stone in water, we see formation of ripples. By the energy you put into the stone and it hits the water, it forms wave. If you understand the concept of it. Production of wave. You have to observe a piece of stone. Drop it in water.
Please do not read this. Don't read screen or explain using the slide.
Okay.
You are reading the screen, please.
So like I explained.
So
Like I explained, when you drop throw a stone into water or a pond or river, you will see the surface bulging out and falls.
We can see the screen. You should face the camera and talk to the audience.
And it falls at a successful interval and dies down after some time. When the energy is finished, the wave disappears and it goes back to its original, and the medium goes back to its original position. There are many other ways can be produced. Another one is ripple sound. Ripple sound is a simple particle that you can practice in the lab. The ripple sound is an apparatus used in laboratory to demonstrate the behavior of water waves. As you can see in the diagram. And now we're going to terminology of waves. There are not three main terminologies, but we're going to talk about wavelength, frequency, period, and amplitude. Wavelength, this is the distance between two successive crests, or two successive troughs. Frequency.
Can you calm down? Hello? Can you calm down? Face the camera. just look at what you want to talk about, then face the camera and talk.
Frequency. Frequency is the number of wave cycles that passes a fixed point per second and is measured in hertz. Period. This is the time taken for one complete wave cycle to pass a point. And the formula for period is 1 over f. And the formula, and it is also the inverse of frequency.
I don't want you to use this thing again. You're just to glance through what you have on the screen and talk to us.
Okay, now we're going to talk about amplitude. Amplitude is the maximum displacement of a point on a wave from its rest position. Now wave speed. Wave speed is the speed at which
You have said wave speed. Can you explain what wave speed is without looking at that screen again? If you look at that screen again, you have a minus, and that's the end of your presentation.
Okay, I'll define it in my own way. Wave speed is basically the distance per unit time a wave it takes a wave to distance per unit time it takes a wave to complete.
Very correct.
Complete its
Circuit. What do you mean?
Phase. This is the portion of a point in a wave cycle. It's a portion.
Is this all you have?
No, I don't.
Yeah, because I am not satisfied with the way you are looking at the screen every time. I am not satisfied.
Okay, I'll start.
Start
Okay.
again from where?
From here. Transverse waves. Transverse waves are waves that move perpendicularly to the direction of the vibration of the wave. Examples are water waves, waves produced by string, and or electromagnetic waves. Now this is a simple diagram of the transverse waves, which consists of, as you can see here, the wavelengths from one crest to another. That is the wavelength, trough, distance, displacement, and the amplitude, the maximum displacement from its rest position. Longitudinal waves. Longitudinal waves are waves that move parallel to the direction of their vibration, quite opposite from transverse waves. As you can also see in the diagram, the wavelengths, as you can see the wavelengths, the amplitude, the compression, refraction, and displacement of the wave. Stationary wave. Stationary waves are formed when two waves move in opposite directions. When two waves move in opposite directions and they have the same amplitude and wavelength, frequency, and travels in the opposite direction.
You have 1 more minute to cover whatever you want to cover now.
Now I'll go to the equation of it. So as you can see on the board, recall that V equals to x over t from the formula for speed. V equals to x over t, where x is the distance traveled and t is the corresponding time taken. Now, for a complete circle, to travel one wavelength t. Therefore, one complete circle is v lambda t. Then v lambda t is equals to 1 over t. Recall the formula of frequency, 1 over f. Then you do subject of formula and everything to find v equals to lambda f. With this formula, you can find wavelength just by making lambda equal to the formula. You can find frequency just by making m equal to the formula also. Mathematical representation of wave motion.
Please, you're wasting too much of my time. Can you go straight? Are you done? You did not explain anything on the equation of the progressive wave.
The equation is
Okay, let's move to your slide. Moving to your slide. Move through your slide. Move through your slide. Next.
Progressive waves are also called traveling waves. This is the wave which spreads out continuously from.
Thank you. I have told you that the next time you look at your screen to read what you are supposed to tell us, that's a minus. Thank you. Next person. So we have another person that will be presenting a work to us. Sure. Okay. Let's see. Check for presentation. Okay, let's have you, Miss Chinenye Okeke. So over to you. Please, I need you to just explain more. I do not advise you, I will not advise you to be reading from the screen all the time. So explain more and be fast on it. Okay. Let's start.
Good morning, ladies and gentlemen, and my fellow
You're live. Please.
Good morning, teachers and my fellow students. My name is Chinenye Okeke. I am a science student. I study at ST&T Regency School. And today I'll be presenting on a given topic by our tutor, Mr. Daniel Adekunle. And my topic is refraction of light waves and application of lens and lens corner. So firstly, we'll be looking at the introduction, starting with the definition of refraction. Refraction can be defined as the bending of light ray as it crosses the boundary between two medias of different densities, causing a change in its direction. Then this diagram illustrates refraction. As you can see, when the stick is placed into the water, it will appear as if it was bent, but in real life, it is actually a straight stick. But when placed in water, refraction occurs, therefore causing the bending of the stick. Then we will also look at refraction through rectangular glass block, and this is a diagram illustrating refraction of a rectangular block. It may be a little bit blurry, but if you look at it, we have the incident ray, and then this is the normal. Then we have the refracted ray as well as the emergent ray. Then we have laws of refraction. We have two laws governing the reflection of light. The first one states that the incident ray, refracted ray, and the normal all lie at the same plane. While the second one, which is under the Snell's law, says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. Then the Snell's law, we have N equals C over V. Then N is the refractive index, V is the speed of ray, while theta is the angle between the ray and the normal to the surface.
I think we cannot see the equations very well. You have a very poor presentation slide. Continue.
Then we're looking at real and apparent depth. So if you look into a pool, the water appears to be shallower than it may seem. This means that the bottom appears to be further up than its actual position. And this happens because refraction takes place. So when we look at this diagram, the fish appears, the real depth of the fish is lower than you may see while looking at a depth at the pool, because there is refraction of course which bend the light waves, causing the fish to seem a bit shallower than expected.
Down.
Then we'll be looking at explanation of the effects of refraction by ray diagrams, and we can see that a stick appears to be bent in water due to refraction. Then we can also see another example of refraction whereby a coin is brought into, a piece of coin placed into a bowl so that its visible can be brought into view by pouring sufficient water to the bowl. And this is due to refraction of the water air interference. So here we see that the rays of light bend here, and then the image of the coin is actually here, but due to the bending of the light, the coin appears to be shallower when seen in the eye. Then we also have reflection of light through triangular prism. And this is the refraction of light through a glass prism. Here we see the normal, we see the refracted ray, the emergent ray, and the incident ray. Then you can also calculate minimum deviation with refraction. So it will be M21 sine in brackets per sine A over 2. Then we'll now be looking at a different aspect of refraction of light. We'll be looking at application of lens and lens formula in concave and convex lenses. Then here we have different types. We have two types of lenses, converging and diverging. We have double convex, plano convex, converging meniscus, double concave, plano concave, and diverging meniscus. Then we'll also be looking at parameters of lenses. We have the principal axis, and these are imaginary line drawn through the optical center, perpendicular to both sides. Then we have the axis of symmetry, which basically divides the lenses into two equal parts. Then these are the terminologies continuing. We have the focal point, we have the focal point, and this is convex and concave lens illustration. And then this is a more simplified diagram of all the parameters. We have parallel rays of light, principal
Can you
axis,
use this?
optical center, and we have the principal focus, focal point, optical axis, and focal length.
What's the focal length?
Focal length is the distance between the focal point and optical center.
Okay.
Then we have the lens formula. So F is for focal length in meters, U object distance, and V is for image distance, and they are all measured in meters. So 1 over F equals 1 over U plus 1 over U. Then we'll be looking at solved examples from WAEC, NICO, and JAM. So it says from JAM 2008, an object placed at the bottom of a well full of clear water appears closer. And this is due to A, diffraction, reflection, diffraction, or polarization. And the answer is refraction, because it is the bending of light as it crosses the boundaries of two media at different density. And it's also due to the fact that apparent and real depth is due to refraction. And And then in the continuation of the solved examples, we have JAM 2010. An object is embedded in a block of ice 10 centimeters below the plane surface. If the refractive index of the ice is 1.50, the apparent depth below the surface is, and the answer will be B because the refractive index is the quotient between the real and apparent depth.
We didn't see the mathematical solution of that question that you just showed us. So how are we going to solve it?
An object is embedded in a block of ice 10 centimeters below the plane surface. If the refractive index of ice is 1.50, the apparent depth below the surface is, so n equals real depth over apparent depth. So when the 1.50 and 10 are substituted, it will give you 6.6.
Yeah, that's what you're supposed to do.
Then we have physics YF from 2019. A ray of light traveling from a rectangular glass block of refractive index 1.5 into F strikes the block at an angle of incidence of 30. Calculate its angle of diffraction. So, using the formula on refractive index, that's sine I over sine R, you can solve it to get the answer.
You can see that we cannot see this. You have seen error in your slide. Okay, move on. Let's leave that.
And then we have physics nickel from 2002. So which color is deviated least when white light passes through a triangular prism? And so the answer would be violet color will deviate the most, but the red light will also show the least amount of deviation. So with that, I've come to the end of my presentation. It may have been a little bit blurry, but questions are welcome from me. Thank you.
Okay. Does your presentation not include the application of refraction?
Under refraction, it should contain application of refraction.
Yes.
But I did not include it in my presentation.
But you know them?
No.
What are the applications of lenses? Because you talked about lenses.
Lenses can be used in glasses. For example, it can be used in sunshades to refract light, as in sunshades are worn to prevent the effect of sunlight, as sunlight can damage the eye. So the type of lenses put on the sunshade will determine the amount of light refracted as it bends.
Okay. In all your slide, I've been able to see just the rectangular glass block solution. But do you know that we have another kind of block, glass block, the triangular glass block? There was no solution for that. We didn't see any analysis of how the rays of light move through the rectangular glass, triangular glass block. You remember, I think I saw an equation. Can you remind me about the equation for the rectangular glass block from triangular glass block? The equation to find the refractive index of a triangular glass block is it?
To calculate refractive index, n equals sine I over sine R.
That's the general formula. But for triangular glass block, there is a special formula.
That was not included in
I saw it. Go to your slide. The beginning of move on, where you have the refraction. Can you wait? Did you see that equation there? That's equation. This is can you see the glass block? You didn't explain that. You just scanned through, and that was the triangular glass block I was talking about, where you have the refractive index from medium 2 to medium 1 or medium. Now you have sine I is still sine I over sine R, where your sine I is the minimum deviation plus the refractive angle of the triangular prism, then divided by 2, or you can write it as sine half or sine D plus A divided by 2 over sine A over 2. So if you have a triangular glass block, the triangular glass block of which is an equilateral triangle, let's say for an example, for instance, so that is A equals to 60. So you're going to input your A as 60 into the equation. Then the minimum deviation, that's what you're going to maybe asked to look for it if you are given the refractive index. And in the case where you're not given the refractive index, you may be asked to look for the minimum deviation of that. Because if you look at the diagram very well, you see that this is the emergent, the incident ray is coming through this interface. This is the air interface, air medium, glass medium. You can see incident ray moves here and refracts through this and emerges here, and that's why we call this, the angle between the normal and the emergent ray is called emergent, angle of emergence, angle of incidence. Then the angle between the normal, you know they say normal here, the angle between normal and the refracted ray is the angle of refraction. And when you trace this incident angle in the block and you trace the emergent ray down where they both meet, the angle formed by the two is what you call the angle of minimum deviation. And that's what you need to have explained to us. That would have given you a good. And then also under your lenses, you're able to tell us the types of lenses and the terminologies, but we did not see the images formed by these lenses, because there are diagrams that explain this. Now you're supposed to explain to us that any ray, because any ray parallel, there are about three rules. Any ray parallel to the principal axis after refraction will pass through the focal point, and any ray passing through the focal point, let's say this is the ray passing after refraction, will be parallel. Then any ray that passes through the optical center will remain undeviated. It will remain undeviated. These are things we are supposed to have seen. You are supposed to show us the image formed by an object at focus, image formed by an object at infinity, the image formed by an object between 2F and C. All these are areas where questions used to come from, and you need to go and work on that. I hope that is for your presentation, but you can work more on it. Thank you. Have a wonderful time. Okay.